be talking about sound. And this is going to include music and the Doppler effect. We'll get to that. No. You're thinking Doppler radar. All right. So, talking about sound, the basis for this entire discussion comes from the wave speed equation, V equals F lambda. And that for any given medium, such as air, the speed is constant. And so as you want to increase the frequency, you've got to decrease wavelength. Okay? We can decrease wavelength by changing the object that is resonating's length. Okay? First of all, anytime an object is creating a pitch or a musical note, that object is resonating. An object producing a musical note is resonating, which has a whole lot of stuff from like last week when we talked about standing waves and the Tacoma Narrows Bridge and playing with wine glasses. Okay, you can always go back and look at that if you need. So the example we're going to use to start is just a simple guitar string. Okay, we take a guitar string and we pluck the guitar string, and the lowest frequency that it could possibly vibrate has it being half a wavelength from one end to the other. Okay? So if I wanted to draw in that standing wave, it would look something like this. And I could say that for the velocity of the wave in that guitar string, it is equal to the frequency times, compared to the length of the guitar string, how long is the wave in this case? It's two lengths of the string, right? Because if this is our guitar string and this is half of a wavelength, it's one antinode, then we should understand that the length of the wave itself is double that length. So the velocity of our wave is frequency times 2 times the length of our string. However, when you pluck a guitar string, it is not just one frequency that vibrates through that string. It also gets additional ones that are or additional standing waves in there that still have nodes on either end. And maybe we could have one that looks like this. I should really raid Lachlan's marker set for this lesson. Okay, and what we wind up seeing is a standing wave that has now produced a wavelength that is equal to the length of the guitar string. So V is equal to F times L, or the length of the string. Okay. Because I'm enjoying drawing these, I'm going to go ahead and throw in another one. I got a brown marker, or brown colored pencil here. Go here to there. I'm going to draw this one back. Okay, and showing the speed of the sound, or the speed of the wave in that guitar string, is still equal to the frequency it's vibrating at times what now? 2/3, because I've got 3 antinodes. I only need 2 of them to make a full wavelength. So 2 over thirds the length of our string. And what I begin to recognize is I'm producing a pattern here. What's the next one of these equations going to be? What's the next equation that I can produce for this guitar string? Say again? Half. And I'm going to write that in a very specific manner. I've got 2 here, I've got 2 here. I can produce V equals F 2L over 4. And what I'm really showing, and if I want to go ahead and fill this one in to fit the pattern, 2 over 2, is that if I want to know the frequency at which the string is vibrating, or the speed of the wave, simply going to be an iteration based on the length of the string and doubling that string and then having some interval number beneath it. So in this equation, V is the wave speed, F is still frequency, length is the length of the string, and this number underneath here, N, is what we call a harmonic number. Our equation winds up showing us that a single string can vibrate and produce multiple frequencies based on a singular length each of those frequencies being a specific harmonic. So harmonics are additional frequencies that a resonator can vibrate at. Additional frequencies that exist within a resonator. A resonator just being literally anything that's resonating. So you pluck a guitar string, you hear a specific note. You match that note on, let's say, a tuba. Okay. Do they sound exactly the same? No. That's because of the harmonics produced. If you were producing just that very lowest or the fundamental frequency, they would sound exactly the same. However, in each of those instruments, the harmonics have different strengths. So each of these additional little standing waves that's produced in that resonator have different amplitudes and therefore contribute different amounts to the sound. So harmonics contribute to the quality of an individual sound, the quality, and if I use this word, anybody know what I mean? Yes? Cool. That's in there for music people, of the individual sound. It's kind of a band thing, yeah. It's another way of saying the quality of the sound and exactly like if it sounds like, well, I don't even know how to describe it. I don't know how to define it. Anybody have a good definition for timbre here? Harmonic here is not what harmonics are in music. In music, if you've got an octave, your harmonics are going to be your bottom note in that key, and then the third, fifth, maybe the seventh within that key. That's not what we're talking about here. Harmonics are simply the iterations that are produced within a singular note that's played by an instrument. Okay, they've got a different meaning in physics than they do in music. Yeah, yeah, you can. All right. For an open tube resonator, meaning an instrument that's open on both ends, this follows the exact same equation because rather than producing a node on either end, we would be producing an antinode on either end. So within some kind of piped resonator, we produce an antinode at either end, and that pipe will then resonate with that frequency. It needs to be an antinode to actually interact with the edges. If we had a node here where it is an open pipe, that sound would not interact with the edges and would not resonate, would not reflect back on itself and create a standing wave within the pipe. Okay? So stringed instruments, viola, violin, bass, guitar, etc. Open tubed instruments such as the flute and like the didgeridoo, I can't think of many others. Those act as open tube resonators that follow this equation. Questions on what a harmonic is? I do want to also write up here n equals 1 is the fundamental frequency of a resonator. Fundamental frequency, which means it's the lowest frequency and the primary frequency that you hear when that object resonates. Okay? Now, we've only described half of instruments here, strings and the flute, basically. Okay? For those of you involved in band, there's a whole bunch of other instruments that we could be talking about. All woodwinds, all brass instruments. I mean, flute's not really a woodwind. They're on mute. So anything that uses a reed, any brass instrument, all fit into this next category, which we call closed tube resonators. Yay. So we're talking about closed tube, what that means is that one of the ends is sealed off. For most instruments, that's going to be sealed off by the instrumentalist's mouth, okay? Or the reed somehow is vibrating at that point there. That's creating a node. That node then creates a wave that goes through the pipe, and at the very end must create an antinode. So if I'm going to follow the same kind of equation pattern from above, we've got our speed of our wave is equal to the frequency we're going to hear, and how many times this length do we need to create the wavelength of our wave? 4. So 4L. And just like above, this is actually per antinode, or based on the individual harmonic. Now there is a huge difference here, and that's that if I try to draw my next harmonic, it looks something like this. Oops, there we go. Okay. So our first wave was what fraction of a wave? 1/4. Our new wave is what fraction of a wave? 3/4. So you'll notice here that in the open tube or the string resonator, I went by halves, half a wave, 1.5 waves, etc. Here I'm kind of going by quarters. What's important here is that the closed tube resonators need both a node and an antinode. And to do that for this setup, n is only equal to odd numbers, 1, 3, 5, etc. Because if I put an even number into this equation, I wind up showing something that's going to create a node at this opening. And that won't interact with the edges, won't cause it to resonate, and it'll just not make a sound. Okay? Only odd-numbered harmonics exist for a closed tube resonator. A closed tube resonator. All right, that means that outside of using a tuning fork, closed tube resonators actually have more pure sounds than an open tube resonator because they have fewer harmonics. So if you want something that's going to have more concentrated fundamental frequency, you want a closed tube resonator. They'll still have harmonics, they'll still be blending more than just one frequency, but not as many as an open tube would. Questions on the difference between these two? Doppler effect. Okay, so again, vehicle sitting still with its siren going, the waves are propagating out in all directions evenly. So from its frame of reference, the pitch is constant, it's a set value. However, if the vehicle begins to move relative to an outside observer, the waves that are in front of it are going to be more condensed, meaning shorter wavelength, higher frequency, and the waves behind it are going to be expanded, so lower frequency, higher wavelength. So let's just put a person here. So as the vehicle approaches, higher frequency. As it recedes, lower frequency. And we can actually say that again. Guys on the sidewalk. Okay. We can then represent this using an equation where the frequency that we observe is equals to the frequency that's emitted if everything's nice and stationary. So to adjust for a moving object, we take the velocity of sound plus or minus the velocity of the observer divided by the velocity of sound plus or minus the velocity of the emitter. E emitter, O observer. S sound. Okay? So in this case, let's say our person is sitting stationary and the car is moving forward. If we have the car moving forward, are we going to hear a higher or lower pitch? Higher. That means that this fraction here must wind up with being something greater than 1, so that the frequency observed is higher than the frequency emitted. So since we aren't going to change VO, since that's stationary, that's going to be 0. If I want to make this fraction greater than 1, do I want to add or subtract VE? Subtract. Why? Right. I want to divide by this, so I want a smaller denominator to make a value greater than 1. So VE is negative for approaching sounds, for approaching sources. All right, let's change up our scenario just a little bit. Our person is walking towards the vehicle. Is that going to cause the pitch to drop back down a bit, or is it going to cause it to go even higher? Even higher, because this person is going to observe these at even shorter wavelengths and so on, then a higher frequency. Meaning that, do we want to add or subtract VO? Add, so I get a higher fraction here, producing even higher FO. So VO is positive for moving towards the source. Towards the source. All right. Because velocity is a vector, this should make sense. This should make sense because take a look at the arrows we drew. The arrows we drew were in opposite directions, correct? Therefore, they should have opposite signs of the velocity. Well, they do. Here, VE is negative and VO is positive. Okay? VE is velocity of the emitter. VO is velocity of the observer. Velocity of sound. Okay? Example of actually calculating what the frequency would be observed for an individual. So let's see here. Nishi is walking at, let's say, 7 meters per second along the sidewalk. And our vehicle here is driving forward at, let's go 30 meters per second. So first of all, because this is an example we already kind of looked at, we should know that the frequency is going to be what relative to the emitted frequency? Higher. Okay, so let's say that it's emitting a frequency of 512 hertz, which is, if I remember correct, middle C. Okay, so it's emitting this sound, and we can find out what sound she hears, what pitch she hears, based on the equation we've got listed here. So FO is equal to frequency emitted, 512, times VS, 343 meters per second. Do I add or subtract the velocity of the observer? I want to add. Yep. So plus 7. Divide by 343, velocity of sound. Add or subtract the velocity of the car. So subtract 30. Okay. So I then, to find my value here, I'm going to have 350 over 313 times 512 is my observed frequency. So 350 divided by 313 times 512, I get 572 hertz. Okay. Everybody good? All right.